Hey guys, can you hear me? Now we are going to learn about the physical chemistry, and the book is Physical Chemistry, Atkins 11th edition, and we are now going to study about the topic 9a, valence bond theory, VB theory, 价键理论, and we first start with the topic 9a.1, the atomic molecules, which means the 双原子分子. And now we will construct a very simple example, hydrogen gas or the hydrogen molecule H2. And as we all know that each electron in an atom can represent by the wave function, and the wave function can be separated to the location wave function, and you can see it here, the location wave function and the spin wave function. And we first talk about the location wave function, and this is two hydrogen atom, two hydrogen nuclear here, hydrogen nucleus, and this is two electrons, and the distance between the first electron and the first hydrogen nucleus is R1 and the other is R2. So we have this formula here, phi 12 is equal to phi H1SA, because the hydrogen atom only has one atomic orbital named 1s, and this is the hydrogen A and this is hydrogen atom B. So if for the convenience of calculation, we represent R1 as 1, R2 as 2. So if we apply the identical particle hypothesis, which means 全同粒子假设, so we will have phi 21 is equal to phi A2 multiply phi B1, and phi 12 is equal to phi A1 multiply phi B2. And this 2 is equal. You can't recognize one hydrogen atom from the other. So we are now going to talk about the key idea of the VB theory. The linear combination of atomic orbitals can present as the molecular orbital, 就是原子轨道的线性组合可以表现为分子轨道. And for the most simple example here, we will have the H2 molecule here. So we will have the sigma bond. Sigma is the most simple bond in molecule here, and its formation process is in this diagram, and this is called the head-to-head because the head of the orbital that looks like collision but a bit different. It's like overlap. It's like overlap, 就是轨道重合. So we construct the linear combination of the atomic orbital. There will be this one. And why there is plus instead of the minus? Plus means the constructive inference. Constructive inference here. And minus means this. And this is the axis, and this is the positive, negative. This is the instructive inference. 这个是相干涉，这个是相消。So there is a knot here, 一个节点. This is also knots, and it has nothing to do with forming a bond, so we choose this one. And this is called the constant of the normalization, 这是归化系数. We are not take too much attention on this one because this is the quantum mechanics. It's only for the convenience of calculation here. You can understand as that. So this is called the valence bond wave function. Okay, let's consider about the spin wave function. This is a similar form here because spin only have two waves. Spin up is represented as alpha and spin down is beta here. So how to choose the sign here? Because the electron is fermion, 电子呢是费米子. So according to the Pauli principle here, we will know that if we exchange two electrons, the spin must change. So phi 12 is equal to minus phi 21, and the total wave function is equal to the wave function of location times the spin wave function. So we have this relationship here. If we exchange the labels, we have these two. And because of the identical particle hypothesis, we know that these two terms are equal. So we will get this relationship. We need to change the signs if we exchange the labels of the spin wave function. So we will have to choose the minus sign here instead of the plus sign there. So this is our spin wave function. We will combine them. We will get the total wave function of the VB bond wave function. So this is the pi bond here, another bond of the VB theory. And it's called face to face because if you look in this side, we will have get this. You see, this is face to face and this is head to head. And we now consider the nitrogen molecule here, N2. This is N and this is N2, right? This is head to head. So this is sigma and these two are face to face, 2 pi bond. This is very clear in this diagram. Okay, but it is one crucial shortcoming of the VB theory. We take a very important example, CH4, the methane. According to the electron configuration of C atom, it should only form 2 bonds because there are 2 single electrons and this is a pair electrons. It can't form the bond. It only forms the lone pair. And we all know that this is the S atomic molecule and this is the PZ atomic orbital. And this is the PY atomic orbital and this is the PX atomic orbital here. When we introduce a very new important concept is about the hybridization. This is called the ground state of the carbon atom. Ground state here, and we now excited the atom and we got its excited state is 2s1, 2px1, 2py1, and 2pz1. One of the s electron will jump to the pz. And now we have 4 single separated independent orbital, and they will combined into a hybrid orbital here. Hybrid orbital here. So H1, H2, H3, and H4. You can see that 1, 2, 3, 4, right? Very clear. So because the s orbital had the spherical symmetry, and these 4 new hybrid orbitals, the length is the same, but they only change the orientations. The length is the same. So when we construct the new hybrid orbitals, we'll only consider the coefficients in front of s and the coefficient in front of all the p orbitals. And we only have to change the sign of each p orbitals here. So how we determine the sign and how we know the relation between A and B. And we will have this relation. We know that from the linear algebra in a vector space. In a vector space, all faces are of normal here. 这个呢，就意思在向量空间中，所有的基底都是正交归一的，就是它们是正交。What's meaning of orthogonal here? This is orthogonal plus normalization, right? Orthogonal in quantum mechanics means their inner product is 0 if these two are unequal. So for atomic molecule, we will have s squared theta is equal to 1. But if these two orbitals are different, for example, spx theta is equal to 0 here. So H1 and H2 also, H4, H3, H4 also of normal to each other. So we will know that this must equal to 0. And we will have we will expand them, and we got these two relationship here, and we only focus on these four terms because the cross terms are all zero here. They are all zero, and let's calculate it about that. Okay, let's calculate it. So it's equal to a squared s squared theta. Because a is the constant, it can move out of the integral, nothing happens. Minus b squared px squared theta minus b squared py theta plus b squared pz squared theta. So we will know that 1, 1, 1, 1 equals to this, right? So we will know that in this relation, because all the coefficients in here, we will assume then they're positive. So we will got A equals to B. And use the normalizations, we will get these four hybrids wave function here. It's very clear, right? And you can check them by yourself. These two are orthogonal, and these two, both of them, each two of them are orthogonal to the other. So you can know if you know H1, H2, then you can know H3 and H4. And it will get you the homework to calculate the bond angle of the methane. This is quite easy if you use this diagram here. Okay, let's look at another example here. And I'm going to introduce one important inference of hybridization. The hybridization of n atomic orbitals always results in the formation of n hybrid orbitals, which may either form bonds or may contain lone pairs. A very important example here is the water. If we use 3B theory, we know that the oxygen p orbital would like this, right? And px, py, pz, and these two hydrogen 1s orbital is approaching to form the water, and it's natural for us to think about the bond angle would be 90 degrees. However, experiments find that the bond angle of HOH is actually approximately 104 degrees. However, if you calculate the homework, if you finish the homework, you will know that the bond angle of a tetrahedral structure would be 109.47, approximately 109. But the bond angle of water is slightly smaller than this value. What happened? To explain this phenomena, I'm going to introduce you the important inequality of repulsive interactions here. Pair-pair repel is bigger than bond-pair than bond-bond. So for water structure, you know the Lewis structure of the water. It contains two lone pairs here. Repulsive interaction between the lone pair is much bigger than the repulsive interaction between bond and pair, so it will squeeze these two bonds into a smaller bond angle, which means the bond angle of the water is slightly smaller than the normal bond angle of a tetrahedron. So we will have 104 slightly smaller than 109.47 here. QED. And this is our whole lesson, and I will leave another homework for you is to use the same procedure to handle the SP and SP2 hybridization and show some examples for me here. Thank you very much, and this is our lesson, and see you next time.